Okay, good afternoon. As usual, I check, can you hear from home? Anybody? Yes. Okay, and you should also be seeing the screen, so we can start. Okay, so what we will do today, we will try to finish Gaussian mixture models, if we manage, otherwise, as usual, we'll bring it with us at least one more half of the next class. Now, we introduced yesterday Gaussian mixture models. Are there questions on what we said yesterday? Then, we introduced yesterday Gaussian mixture models. We said that the density is defined as a weighted sum of Gaussian densities, and then we gave an interpretation of these terms. Essentially, we interpreted the model as representing the marginal of a joint density. The joint density represents the joint density of the feature vectors x and what is called an unknown or unobserved latent variables that represents a cluster label. We said we can interpret the GMM as we are modeling our data as if it was made up of clusters. Now I don't use colors because clusters are not necessarily classes, and they may not be necessary things that we can clearly see as subclusters. The model will find clusters that it deems useful to maximize our likelihood, but we can imagine that there are clusters which may also overlap. Each of these clusters can be described in terms of a Gaussian and a prior probability of the class. So we can imagine that a sample of our training set is obtained by first throwing a dice that gives us the cluster number. Well, an unfair dice because it will give the cluster number with a probability that is pi k, that is actually wk, the weight of the corresponding component. And then, having chosen the weight, to generate the actual sample, we will draw a sample from the Gaussian distribution. So essentially, to create the dataset, you can imagine that if I have n samples, I've run this procedure n times. To create the samples, I have created n. I have, for each sample, selected randomly the cluster and then created a sample from the corresponding Gaussian. Once I look at all the samples together, of course, I just see this. Now, the goal of the model is, we assume that that's how the samples were produced. We want to find the parameters of this distribution. Why? Because that then allows us to describe the overall distribution of the samples. Again, we don't know the cluster label, but what we care here for the GMM is to find the density of the marginal density. So we don't care to find the joint. Well, we will actually know the joint, but we don't care about the cluster label of the samples. Our goal here is okay, can you hear? The microphone was dead. Can you still hear from home? I changed microphone. Yes, somebody's writing, so I guess it's yes. Okay, as I was saying, our goal is not finding the cluster label, even if it could, if we want to perform clustering, we'll see how to do that. But our goal is to use this model to estimate the overall density, so we are interested in the marginal. But we said that directly optimizing the marginal density is not directly, well, it's feasible, but typically will not work very well. So we are trying to figure out a way to learn the parameters of the cluster models, of the model. So not the cluster labels that will be associated to the train set, but what we want to learn is the mean and covariance matrix of each Gaussian component and the corresponding weights. Now, we have said that if we knew cluster labels, then everything would be easier. If we knew the real cluster label, so if I told you these samples, if I color these samples and tell you these samples were generated by component 2, these samples by component 3, and these samples by component 1, then it would be easier to find the mean and covariance of each component. We would just treat this as if it was a classification problem. Each cluster would correspond to a class. We would fit a Gaussian density for each cluster. We'll find the mean and covariance matrix of the samples of each class. So, for example, we would find mean and covariance for the blue, then mean and covariance for this should have been black, mean and covariance for this should have been green, and so on. I tell you what is the cluster label. You can pick the samples of each cluster and estimate the corresponding mean and covariance. And then the weights are also simple. In this case, the weights are the prior probabilities of the classes on the training set of the cluster. What is the prior probability estimate for the training set points? Well, that's the maximum likely solution for a model that tells me what is the probability that I selected cluster K. If cluster K has K elements out of N, we already know from our analysis of multinomial, from when we discuss multinomial models, that the maximum likely solution for a multinomial model is the frequency of the corresponding of the elements that correspond to that specific outcome. So in this case, the outcome is the cluster label. The cluster label can be modeled as a multinomial density, so the maximum likely solution would be the number of samples for each cluster. Unfortunately, we don't have the cluster labels. You don't have anybody who tells you the cluster label. So let's make a different step. Let's imagine that now, rather than giving you the cluster labels, I give you a set of weights and mean and covariance parameters for each component. Now, again, this requires me to give you this information. Now, imagine I give you this information. What can you do with this information? Can you find the cluster labels? Can you find the cluster labels for a sample X? I want to find its cluster label. How can I do that? I know that each cluster is described by these parameters. These are the components of the Gaussian, and this is the prior probability that the sample belongs to that cluster. We can compute the cluster posterior probability and then take the cluster, the maximum. The highest, the posterior probability for cluster K is what? It's the prior probability for cluster K times the cluster conditional probability for cluster K. Here we use the word cluster, but there is nothing different from when we were doing classification. Here we have cluster and we want to find the cluster label. So in this moment, in this specific moment, there is no difference with what we were doing with classes. We can treat the cluster as if they were classes and do the same thing. Here below, we would have what? We would have the marginal. The marginal is exactly the GMM densities, the sum over all clusters of the joint cluster and feature probability. Density, not probability, but pass me the word probability. This is exactly the GMM density for sample X, given the set of means, covariance matrices, and weights. So these are the set of all the sigmas, all the means, and all the weights. We have everything to compute this. I gave you the weights, I gave you the means, I gave you the sigma. You're computing it for some sample X, so you can compute it for all the clusters, for cluster 1 up to cluster big K. So this, in this case, will become cluster 1. This will go to big K. And then one possible way is to decide to label the samples as belonging to the cluster which has the highest posterior probability. So this is one possible way. This we already know how to do it, and then we could try to ask something. How can we use this process to try to get an estimate of the mean and covariance and weights of a GMM? We know that we see that this is not the best possible approach, and we will discuss why. But for the moment, let's say, okay, if we have mean and covariance and weights, we can associate a cluster label to the samples. If we know the cluster labels, then we can estimate the mean and covariance of the different samples. Can we try to combine the two in some way? Let's imagine I have some initial estimate of the mean and the covariance, which are not necessarily very accurate. So they may not be a maximum likelihood. When I say maximum likelihood, in this case, of course, I mean local maximum of the likelihood. We discussed why yesterday. This may not be a maximum likely solution. For example, one Gaussian may be here, the other may be here, then I maybe have a third here, a fourth here. These are not a good fit of the samples. But let's imagine that I start from this point. Can I use the strategy to find a better solution? Well, one possible way would be if I have my initial set of means, covariance matrices, and weights, I could try for each sample to compute sample xi to compute a cluster label ci by predicting the maximum over the cluster labels by predicting the cluster label, as we said before, for all the points. So for each point, for each sample I will compute cluster posterior probability for all the possible clusters, as we have said. So I have point xi. I will compute probability that the cluster is k given xi, probability that the cluster is 1, probability that the cluster is 2 given xi, in this case up to 4, if we have 4 components. W1 normal of xi mu1 sigma 1 divided the GMM density. The same W2 normal of xi mu2 sigma 2 divided the GMM density. Notice the denominator here is always the same, so I don't really need to compute it. But then I take the maximum of this. The maximizer of this will be the label Ci star that I associate to the sample. So I start with my training set, an initial set of parameters, and I can use this to estimate a cluster label for each sample. Okay? Now, what do I have? I have a data set that I can imagine being a data set that contains both samples and a cluster label. The cluster label is the one that I predicted. But for now, I can forget that that's the label that I predicted and take that as if it was the correct label for the cluster. We know that if we use these labels, we can re-estimate a new set of model parameters. So from this, I can compute the maximum likely solution that gives me a new set of model parameters. How? Well, essentially, I will split my data in clusters. So I will take all the points for cluster that have been assigned to cluster 1. So all points I for which Ci star is equal to 1. Then all points for which Ci star is equal to 2. So I divide my data set into partitions based on the cluster label. And then from this, I compute mu1 by simply taking the average of, for example, for the mean, the maximum likelihood we know is the average for the samples which belong to that cluster. So I take the samples of cluster 2, for example, I sum them, I divide them by the number of samples that have been assigned to cluster 2, this is the maximum likely solution for the mean when the cluster labels are these. So assuming that the cluster labels are correct. So if I assume that these are the cluster label, then the maximum likely solution for this dataset that includes both the X and this artificially generated cluster label is the maximum likely solution that we already know is obtained by partitioning in clusters, and then for each cluster fitting a Gaussian to the samples of that cluster. Now, we can imagine that if this works well, we may have hope that this will have improved our model. We don't know whether this will improve our model, but we may hope that this will give us a better estimate. Why? Well, let's see what will happen on that example. Let's start with these 4 Gaussians, and let's imagine these 4 Gaussians all have the same covariance matrix, so that we don't need to care about the covariance. Actually, let's say we don't re-estimate the covariance, we fix the covariance matrix for the components to be the identity. We have the full model, but nobody forces us to estimate all the parameters of the model. We may decide that some parameters of the model will be fixed to some value. So we get a maximum likely solution for the remaining parameters. Then in general, we will re-estimate this as well, but keeping it fixed simplifies the operations. Now let's color them. Let's make this blue, this green, the other red, and this one black. Now let's try to assign a cluster label to the samples. What will happen? These points are, since sigma is the identity, essentially cluster labels, posterior probability are proportional to the distance of the point to the class. Because it's for all the classes, it's exponential of minus 1/2 x minus mu k to the square. When I take the log, the log posterior probability is equal to this plus some constant that I don't care about. So essentially what defines which is the maximum is the lowest of the distance of a point from the mean of the correlated Gaussian. So these points will be assigned to the black cluster. These will be assigned to the green. Probably this one will also be assigned to black. This will be assigned to blue. And this, sorry, blue, not black, blue. And finally, this is far from everything. Let's say it's still assigned to red. So let's keep it red. Now, what happens if I try to find the mean of the new components? Where do they move? Well, the mean for the red moves here. The mean for the blue moves here. Still, the covariance is fixed to identity, so it's a component like this. The mean for the green moves here, and the mean for the black moves here. So we see that overall we have a better coverage of our training set. We can think then, okay, since we improve our coverage, why can't we repeat the process? We have a new set of mean, sigmas, and weights. We repeat the process. With this new set, we compute a, let's call it 1 now, because they're computed with the parameters 1, set of cluster labels for the different samples. These are computed using these parameters for the Gaussians. So we take these Gaussians, and assuming this represents the clusters, we compute new cluster labels for the samples. Then we have new cluster labels, the original samples. We can again estimate a new set of mean, covariance matrices, and weights. So essentially, we can try to iterate between, we take model parameters and estimate cluster labels, then we take the estimated cluster label as if they were correct, and we estimate a new set of the parameters. Then we need to prove that this will converge to a good solution, and we will actually observe later today that it does not necessarily converge to a good solution, but intuitively it's already going in the correct direction. We see that the correct way to finding a local maximum of the likelihood is not that different from this. But this is probably easier to understand. So the idea here is I have a set of parameters. I don't have cluster labels, so I use this set of parameters to compute cluster labels for all the samples with these parameters. And then with this, I will compute a new set. Sorry, zero, no, a new set of parameters. W. Then from this, I will compute new cluster labels and compute a new set of parameters. Then compute new cluster labels and then compute a new set of parameters. And I can iterate until, well, hopefully, I hope that I will not start oscillating between different solutions. So I hope that this will at some point converge to a solution. And if it does, then I will stop when I will reach some convergence criterion. Now, I'm not sure whether you can prove that it always converges, but if I remember right, it should. But that doesn't matter because in the end, we will not use this strategy because we will see that we can do better than this. But why do I show this? Because, well, this is fairly easy to understand as a process and because it has several connections with things that you have seen. Well, let's go through the steps again. We start, so this is something that I already said. When we have a given set of parameters, the step is we compute cluster labels for all the samples. And then from this cluster label, we compute a new set of parameters. How? Well, computing the new set of parameters, we said it's similar to what we do for the multivariate Gaussian classifier. Let's see also mathematically that this is true. When we treat cluster assignment as if they were labels, we can write our log likelihood. The log likelihood is, in this case, since we have both xi and ci star, we treat the ci star as data, our log likelihood is the probability, or better, the density of all the training set values, which include the original values and the now synthetic labels that we have assigned to the cluster. So what we are doing here, we treat these as if they were real data that we observed. And we will see that this is the problem that does not ensure that we find a very good solution. But we will overcome this later. For the moment, we treat these as if they were real cluster labels. And then the likelihood for our data set is what? Is the density of everything that I have observed. Again, I assume independence. Samples are independent and identically distributed, so the overall likelihood is a product over the different samples. And then all the samples have the same distribution, so this is the likelihood function. It's a product over the samples of the joint density of a sample and the corresponding cluster label. That's the same we were doing with the Gaussian model at the beginning of the class, of the course. These were class labels. In this case, these are the cluster labels. But the density expression is similar. Then we pass to the logarithm. This becomes a logarithm of joint densities. Now we factorize the joint density according to the model. The model tells us that we have a class conditional that is Gaussian with parameters given by the Gaussian component that we are considering, and a prior probability, the prior probability that C is equal to Ci star is W Ci star. Is the weight of the component, the cluster label. This is the likelihood that we have to maximize, which consists, once we put inside the values of the model parameters, in this expression. Notice the similarity with the MVG likelihood. In the MVG likelihood, we didn't have this term because the prior probabilities were not a model of the parameter of the model. In the MVG classifier, the class prior probability are not a specification given by the model, but it's something that we plug from outside. Here, the cluster prior probability instead are part themselves of the model, because it's the model that will partition the data into clusters. So it will also define which is the probability that a point belongs to one of the clusters that the model will find. So in this case, this term is part of the things that we need to estimate. In the MVG, this will be log probability of the class, but since it does not depend on the parameters, it was a constant with respect to our model. But apart from this thing, we can observe that indeed the first part, we have two parts here. The second part depends only on the weights of the components, and the first part depends only on the Gaussian, on the parameters of the Gaussian components. And this first part looks exactly the same as the log likelihood of an MVG model. So the solution for this part will be exactly what we said before. The solution maximizing this part with respect to these parameters, of course, since this part does not depend on mu and sigma, when I maximize with respect to mu and sigma, this part is irrelevant. I can independently maximize these two terms on their own. The first term is the log likelihood of a multivariate Gaussian model, where the class labels are now the cluster labels. So we already know the solution. We take the samples that have been associated to each cluster, and we compute their empirical mean and covariance matrix. We already know how to do this. The second term has this expression. We need to find the maximizer of the sum of what? The sum over samples of the logarithm of the W of the corresponding cluster label. How can we represent it in a compact way? Well, this sum can be expressed as a sum over clusters of what? Well, essentially, it's the same we did when we discussed the multinomial model. If I have three samples with Ci star 1, Ci star 2, let's make 4 samples, Ci star 1, Ci star 3, and Ci star 2 again, let's call this 1, 2, 3, 4, and 5, then this sum will be what? Log of W1 plus log of W2 plus log of W1 again plus log of W3 plus log of W2. So each weight will appear how many times? So weight 2 will appear a number of times equal to the number of samples that have been assigned to class 2. So the number of samples that have been assigned to class 2, I can write in this way. If C is the cluster that I'm considering, let's make 2. W2 will appear a number of times equal to the number of samples, which I can write, I sum W2, well, I sum log of W2, a number of times equal to the number of samples assigned to cluster 2. Now, I had a sum over samples, I can transform this as a sum of all clusters. If I span over all clusters, I will be counting all the samples. So the sum over samples is a sum over clusters of the contribution of the samples of that cluster. And in that case, cluster K is a generic cluster. So I can rewrite this in this way, where I have two summations that run the first over cluster, the second over the number of points in that cluster of this term. If you prefer, I can rewrite it as a sum over cluster of the number of samples of the cluster times logarithm of WC. But this is the log likelihood of the categorical model. We have seen it when we were discussing multinomial classifiers. This is exactly the kind of log likelihood we had for a categorical model. So we already know how to find the maximum solution of this. It's the frequency of samples that have been assigned to the cluster C. So the weight WC will be, the maximum likely solution for WC will be number of samples assigned to class C divided total number of samples. This is the total number of samples. The sum over the clusters of the number of samples assigned to each cluster is the total number of samples. So we know already from previous lectures, and if you don't, you need to revise the previous lectures, how to solve this problem. So we know how, now we have all the steps to do everything. Given an initial set of parameters, well, we still need to decide how to find a good initial step of the parameters, but initial value of the parameters, but given an initial value of the parameters, we know how to compute cluster assignments for that set of parameters, and we know how to maximize the likelihood as, well, maximizing the likelihood, I mean maximizing the likelihood that I would have if these were the real observed cluster labels for the samples. By repeating this process, we will hopefully reach a point that will provide us a good model for our feature. Does it? Well, let's see with an example. This example, we have the three components that I was showing you yesterday. We start with an initial GMM which has three Gaussians. The three colors correspond to the three components of the model. And why they are smaller? Because each of them is already weighted by the corresponding weight. So the sum of these three curves is the density. Each of these represents already W1 times the normal. So the curves do not integrate to 1, but each curve then integrates to its corresponding Wi. The area below the red curve is equal to Wi. So each of these is already one component multiplied by the corresponding weight. And the sum of these, the dashed line, is the overall density that is obtained by summing these over components. The first step, I compute cluster posterior probability. I plot histograms, so I will color my samples according to the cluster label, and the histograms will be colored accordingly. Here there are bins that have both colors. Why? Essentially because bins are discrete. If a bins like this has this color, that means that at some point, half of the points were assigned to the red component and the other half were assigned to the green one. But when I plot the histogram, they appear at the same bar that is overlapping because the histogram does not have the resolution to tell these two apart. So just ignore the edges. The edges means that a part of those samples belong to one cluster and a part belong to the other cluster. The rest tells us what are the clusters that have been assigned to the samples. Then what I do, I fit one Gaussian to each cluster. So I treat these as if they were three data sets. You see the histograms are rescaled because now I treat each set of points as if it was its own data set. So I plot the corresponding density histogram for each class. So now each histogram area is equal to 1 because I want to see how well my component will fit that particular histogram. And I fit a Gaussian histogram to each of these three sets. And then I estimate my weights. Here you don't see the weight estimate. The weight estimate would be proportional to the size of the original histogram that I was showing above. So here the histograms have been rescaled so that all the three classes have an area that corresponds to a density. The weights would correspond to the proportion of the samples that were assigned to the different cluster in the original image. If I put everything together, again, this is the density that I would obtain. And if you want, in the next slide, you can see the different components that make up the model. We have a small red, which means we have a red Gaussian that is thin and there's a small weight, which models the central part of this histogram, and then these other two components. Then I can repeat the process. If I repeat the process, you see that now the area that is being assigned to the red cluster enlarged. That's the region. How do I compute that? Cluster posterior probabilities are proportional to joint. This represents the joint, so the area assigned to the red class is the area where the red curve in this plot is higher than the other two. So this region, in this region, the red curve is higher. The red is equal to the joint, so Wi times the Gaussian for the red, which is the joint. The joint is proportional to the class posterior, so the winner is the curve that here in this plot is higher. So everything that is where red is taller than the other two will be assigned to red. Then I do the same. I have this assignment. I extract those three as if they were three different classes. I fit a Gaussian to each of them, and this is the result that I get for the components. I compute the weights again as the fraction of points assigned to each cluster, and putting everything together, you get the result at the bottom of the slide. then I can proceed with this operation. You see that my components will start moving. At some point, the red one will find its place in the between. The other two will also adjust to better model the two tails, and this is the result that I get at the end. You see, it's good, but it's not perfect. If you go back to the original slide, the initial slides, this is a GMM that does a good fit. This is the GMM obtained from which the data was sampled. So here I'm plotting the density of the model that I used to generate this data. So we can see that it finds a good solution, but it's still not perfect. There is still something weird here, where there is an overestimate of the density. Here it's underestimating the density. Here again, it's a bit overestimating. So it's good. It's much better than a Gaussian. A Gaussian would just do like this, but it's still not perfect. Now, why it's not perfect? Well, we will see in a moment. The reason it's not perfect is because we are essentially, at each iteration, we start from model parameters. We associate a cluster label to the samples, and then we treat that cluster label as if it was correct. But imagine a case where I have two Gaussian components like this, and a point, sorry, red, and a point that is in between. To which of these two components should I associate this point? Well, I associate it to the red or to the blue. Well, maybe if it's a bit to the left, I will say it's red. If it's a bit to the right, I will say it's blue. But in any case, there is a high chance that I'm wrong. If this was a classification problem, there is a good chance that I may be wrong, because this point is a point that is near the boundary between the two components. So what is the correct cluster that generated it? There is more or less the same probability that, remember how I generate samples. When I generate the samples, I randomly select the cluster, and then I select a sample from the Gaussian. I generate a sample from the corresponding Gaussian. So the probability that I generated it from the red cluster and the probability that I generated it from the blue cluster, these are exactly the posterior cluster probabilities, are similar. So a point that lies here, I may say it's from the red cluster, but there is an almost equal probability that it was generated from the blue cluster. But when I say it's red, then I take that as certainty. So for me, it's the same as a point that was here, which is almost surely generated by the red cluster. Not surely, because there is a small chance that it comes from the blue, but it's very small. How can we address this? Well, let's give an intuition. Let's imagine I have several points in the same region. Well, one possible way I could say is, okay, I know that these points, they have more or less the same probability, 1/2, of being generated from the two classes. So I can say, okay, I will associate half of them to the red and half of them to the blue. Maybe if there are lots of points in this region, then maybe I don't even have to do anything. More or less half will be close to the red, and more or less half will be close to the blue. The problem is, if I have a single point, then what should I do? I should essentially split this point in two and say, okay, since these points can be from both clusters, I will associate half of this point to the red. Red is this one. Why those? Red component, and half of the point to the blue component. So what we will see is a method that allows us to do exactly this process. We will be splitting our points, and in case like this, we will see that our split will correspond to saying, okay, half of this point belongs to the red class, so I will use half of this point to estimate the parameters of the red Gaussian, and half of the point will be used to estimate the parameters of the blue Gaussian. This will give us, we will see, a solution that works much better. Now you may wonder how I can assign half point. We'll see that in a moment. Before we see that, however, let's still stick with the procedure that we have seen up to now. The procedure that we have seen up to now was, we have some points, we have an initial set of components. Then we assign each point to one component, and then we re-estimate the parameters of the Gaussian. Now, let's consider a simplified problem where we fix all the Gaussian covariance matrices to be identity, and we also fix the weight of the model to be 1 over k. That is, we force our model to be a model that is defined in this way. The only parameters that we estimate are the means of the Gaussians. Nobody forces us to estimate all the parameters, of course. This may be a worse fit than if I estimated anything, but it's still a valid model. I can train a model where these are the constraints that I want to meet. Now, let's see what happens in this case. We said already that cluster assignment corresponds to finding the maximum of the class posterior probability. But the posterior probability is what? It's the joint, it's proportional to the joint. So the maximum of the posterior is the maximum of the joint. The joint is the conditional times the prior. The prior is 1 over k, so it's the same for all classes. Sorry, let's not use k. Let's use small c here. This is large k and this is small c. 1 over k, which is a constant, so it doesn't affect the maximum. I can throw it away, it will not change which is the maximum of the class posterior. It's the same regardless of the cluster. So what decides is the max over the maximizer of the class conditional. But the class conditional, I can take the log because maximizing the condition, the density, or maximizing the log density will give me the same answer, is exponential, is logarithm of exponential of minus 1/2, so it's minus 1/2 x minus mu c to the square. The sigma has disappeared because it's identity, which means that it's the same as taking the mean and putting a plus in front here. Minimizing minus the norm is equal to maximizing minus the norm is equal to minimizing the norm. Then I can throw away the 1/2 because that's a constant. Result, the assignment can be obtained by finding the cluster whose mean is closest. But then, what does our algorithm become? We start from points, from means that we now call centroids rather than means. Then, for each sample in the dataset, we assign that sample to the component whose mean, so whose centroid is closest, and then we re-estimate the means. So we re-estimate the centroids. How? Maximum likely solution. The mean of the samples that have been assigned to that component, so to that centroid. And then we repeat. So we start from centroids. We estimate cluster label by finding each point to which is the nearest centroid to each point. And then we re-estimate the centroids by taking the mean of the points assigned to that centroid. This is, I hope you remember, exactly the k-means algorithm. So the k-means algorithm is exactly the procedure that we applied for a specific kind of GMM. Now, this procedure that we applied for the GMM is called estimation of the GMM through hard assignments, because we essentially assign each point to a single component. And the k-means is a specific implementation of this algorithm where we assume the covariance matrix is the identity and the weights are the same for all the components. Which also means that we can see GMM as a generalization of clustering of the k-means. A generalization that allows us to have clusters of different dimensions. The prior for the clusters can be different and can have also different shapes. So we may have clusters which are oriented in some way and clusters that are oriented in a different way. So if we have, for example, a data set which looks like this, k-means will have problem figuring out that there is a slice like this, a slice like this, and one like this, because it assumes the covariance matrix of all the components is the same, the GMM may be able to identify these methods. Not only that, the GMM may also help in finding a solution that gives us soft assignments, that is, it does not just give us the cluster label, but gives us the probability that a sample belongs to a given cluster. So we can, with the algorithm that we see now, learn a GMM, and once we have learned the GMM, we can still, if we want to do clustering, assign cluster labels using cluster posterior probabilities, but we will have, first of all, a GMM that is learned to maximize the likelihood, so to better fit the data, and a model where the cluster may have wildly different sizes and different shapes. Of course, the shapes are constrained by the shapes that a Gaussian density would find as. Yes. Yes, of course, we will see. Yes, we will see how to choose that at the end. Of course, the final results depend on the initial parameters. So at the end, we will see how to select. We said, let's leave that open. Now we will say, I give you an initial set, we will find the solution. Then at the end, we will see how to find a good initial set of parameters. Now, let's go back to our problem, and let's now try to address the issue that we have when we assign cluster labels based on the model parameters themselves, and then we treat those cluster labels as if they were real observed values. We know cluster labels are not real observed values because we don't really know the cluster label. What we were trying to do is generate synthetic cluster labels, and then we were trying to use as if they were real cluster labels. But that led to the problems that we have seen. The model was not that accurate in some parts of the estimation of the density. So let's now go back, and as I said, what we will see is a way that assigns fractions of points to different components and finds the solution with this fraction of points. We will see now an intuitive way to derive this. Then we will see a general algorithm that proves that this method will find a local maximum of the likelihood. We see the algorithm in general, and then we will apply it to the GMM, showing that it's exactly the same as what we are going to discuss now. But let's start again with something that is a bit more intuitive, even though, as I said, with respect to the formal proof, it may arise questions like, why would we do exactly that and not something slightly different? Why we will need to prove it, why this works well. But let's, for the moment, look back at our likelihood. We want to optimize this likelihood. This is the likelihood for the really observed variables. The only observed variables are the xi, the feature vectors. The cluster labels are not observed variables. So the likelihood is the density of the observed variables. So the GMM marginal computed over the features. Which had the problem, we said that we have this expression, which is a sum of exponential terms inside a logarithm. So we try to take the gradient, the derivative of this, then it's difficult to find an expression mean of component C equal to something. But let's try in any case. Let's take the gradient of this expression with respect to the mean of class C and set it equal to 0. Now, I'm not going to prove it, but it's not that difficult to prove it. The sum over I remains when I take derivatives. Then I have derivative, because derivative of a sum is the sum of the derivatives. Then I have derivative of a log. I have 1 over whatever was inside the log. And then I need to take derivative of this term. The outer sum is a sum of components. Only components C will depend on mu C. So this sum disappears because only the terms that refer to components C will actually remain. And then I need to prove it. WC is a constant, so it remains. I need to prove it that the derivative of the Gaussian with respect to the mean is equal to this term. Again, for that, you can try to write the expression of the mean of the Gaussian component, of the Gaussian density as a function of the mean. either as a vector if you're brave, or as a single element of the mean vector, write it down, then re-put everything in vector form, and you will find that this is the expression that you obtain. I don't care that you are able to derive this, as I said. But this is the expression. And now this expression is interesting because this term we already saw it. What is this term? It's the posterior probability that the sample is from class small c given the sample xi. We call this also responsibility gamma ci, to avoid writing every time all the posterior. So we have this minus comes from, I don't remember where, from the fact that this is an exponential of minus 1/2, etc. But it's not important because you set it equal to 0, so the minus as well disappears. We have the important term is this. We have a sum of what? Sigma c xi minus mu c weighted by the posterior probabilities. And this should be set equal to 0. We can solve it as a function of mu c. This tells us that for this to be true, mu c should be equal to this expression. Now, did we solve the problem? Did we find a solution for mu c? Looks like we did, but this gamma ci, to compute it, what do I need? This gamma ci is itself a function of mu c. So what I wrote is mu c equal a function of mu c. So I need to solve this expression. But now let's do as before. Let's say that you find me who gives you the gamma ci. So I give you the posterior probability for the cluster. Before I was giving you an initial set of parameters and find the posterior probabilities. I told you if I give you the cluster labels, then you can find the means. Now I give you this gamma ci. I tell you what are the gamma ci for the correct solution. I don't give you the means, but rather than giving you the cluster label, I do something even better. I give you the cluster posterior probabilities for all the samples and for all the clusters, so all the gammas. Now, if I give you the gammas, you can compute these terms. So if I give you cluster posterior probabilities, you can compute mu c. It's a weighted sum of the samples. And notice that it's an interesting expression. Each sample is weighted by how much? By the corresponding cluster posterior probability. And I divide by what? Each sample, here I have a sum of the samples weighted by the posterior probability, and here I have the sum of the posterior probabilities, which corresponds to what? Well, if I imagine that sample xi has been assigned to cluster C for a fraction equal to this term, so for sample x1, I will have this term, this fraction. Then for sample x2, I will have another fraction. Then for sample x3, I will have another fraction. And I take the mean of the fractions that have been assigned. It means that my solution will be gamma c1 x1 plus gamma c2 x2 plus gamma c3 x3 divided by what? Divided by the amount of samples that have been assigned to cluster 3. But what are these amounts? Are the sum of the fractions of the samples. So divided by gamma c1 plus gamma c2 plus gamma c3. If I split the points and then I say this fraction is assigned to cluster 1, this fraction is assigned to cluster 2, and this fraction is assigned to cluster 3, what is the average? Is the weighted by fractional sum of the samples divided by the amount of samples that have been assigned to that cluster, which is exactly this term. So the mean is a weighted mean, which I can interpret as I have assigned only the fraction gamma ci of the sample xi to the cluster C. So if I give you cluster posterior probability, this is exactly the solution. If you know the correct cluster posterior probabilities, then the solution consists essentially in considering a point belonging to the cluster for a fraction that is equal to the cluster posterior probability. This is for the mean. Now, for this to be true, we will need a similar expression for the covariance matrix. And as you can expect, that's exactly what we will find. If we were to write the solution for the covariance matrix, we will find a similar expression. Before we see the solution for the covariance matrix, let me introduce a couple of terms. The sum of the responsibilities is called zero-order statistics. Remember that for the Gaussian model, we said the zero-order statistics were the number of elements of the dataset. Here, the zero-order statistics for cluster C is the fraction of samples assigned to those samples. And the first-order statistics is this weighted sum of the samples. The mean corresponds to what? The ratio between the first-order and zero-order statistics. Now, for the covariance matrix, we are not going to prove it, but we can show that the covariance matrix will be, again, a weighted sum of the contribution of the different samples. Each sample will contribute for a fraction equal to its own posterior probability. So again, even when computing sigma, a sample is behaving like that fraction of the sample was assigned to that component. In which way, essentially, that fraction of the sample will contribute to the zero, first, and second order statistics. Now, second order statistics are actually defined by this expression, and we can show that the covariance matrix can be obtained by taking second order statistics divided zero order minus the mean times the mean transpose, but this is not particularly important. It's just that typically you don't represent directly the covariance matrix, but we will see that we will compute second order statistics, and then the covariance matrix itself, we will find it as a byproduct of the second order statistics. But we see that both in the first and second order statistics, each point contributes for a fraction proportional to the cluster posterior probability. And as you can imagine, the maximum solution, likely solution for the weights would now be, we are not showing it, but the fractions of samples assigned to that cluster. So the zero-order statistics, so the sum of all the fractions assigned to that cluster, divided the total number of samples. That is also the sum of the zero-order statistics. So if I give you the cluster posterior probabilities, then that's exactly as I said, we have a solution where we can interpret each point as contributing to the corresponding cluster by a fraction proportional equal to the cluster posterior probability. The problem is we don't know this. But does this stop us? What did we do before? We didn't have the cluster label either, but that didn't stop us to try to figure out a way to get them. You don't have this, but let's now say that I give you an initial set of parameters. So an initial set of weights, bit large. Weights, means, and covariance matrices is 0. If I give you this, you know how to compute posterior probabilities for all clusters with this set of parameters. We were doing this before already. To compute the new cluster labels, we were computing exactly this term and then taking the maximum over C. So the CI we were using before star was the argmax over C of these terms. So we already know how to compute this. Each of these terms, we are not doing this argmax operation anymore, but each of these terms is computed by taking WC normal for xi, we're using sample I, with mean mu c 0, sigma c 0, of course these are all 0 because they are the current parameters, divided the sum c prime of wc prime 0 normal of xi, mu c prime 0, sigma c prime 0. So we were already doing this in the previous model, in the previous procedure. We needed this to compute cluster labels, so these are the same terms. Now we don't compute cluster label, we use this and we apply the procedure that we have just seen. So rather than splitting the dataset into k clusters, now for each cluster we consider all the samples, but all the samples are differently weighted according to the cluster we consider. So for cluster 1, we will have that all the samples will be considered but with these weights. So all the samples of the dataset contribute to cluster 1, maybe with very small weights, but the weights will never be 0 because the density is never 0. If the prior probability of the cluster is on 0, then the posteriors cannot be 0. So each point, even very small, very little, will contribute to all the components with these weights. What changes from component to component is the weight. So for the second component, I will have different weights, and so on. So I will use all the samples to estimate mean and covariance of each component. How? Well, using the corresponding weights estimated for that component. So for component 1, mu1 will be the sum of gamma 1i xi divided the sum of gamma 1i. For component 2, the mean will be the same, 2i, but this time with the weights that I estimated for the second component. Notice that this sum runs over the whole data set every time. All the samples are used for all the components of each cluster. So we are not partitioning the data set anymore. We are changing the weight that we give to each sample for each cluster. But all the samples will contribute with a different weight to all the clusters. And we can see this in action. You will see that at the beginning it will be a bit slower with respect to the other method, but then it will give us a much better solution. Now, some explanation of the coloring because it needs a bit more of explanation. The first image is the same as before. The densities of the different components multiplied by the weight, and the dashed line is the overall GMM density. But now here we have 3 overlapped histograms. What do they represent? Well, remember that each point is assigned to each cluster with a weight. So this is the sum, the height of this bar is not the number of points that have been assigned to that cluster, but is the sum of the fraction of points assigned to that cluster. In each position, we will have that fraction of points will be assigned to all the cluster. Just the proportions will be different. So for example, in this region, let's see, large fraction of points are assigned to the red. We have large fraction of points assigned to the blue, and somehow smaller fractions of points assigned to the green. So for points in these bins, the posterior for blue classes may be 1/2. The posterior for the red is maybe 1/3, and whatever is left, 1/6 for green. If we move here, we see that for a point in this position, then the posterior for green is probably 1/2. I'm making up the numbers. It's maybe not exactly 1/2. But then the posterior for blue is probably, I don't know, 1/4. It's not exactly correct, but and then the posterior for 4 is also needs to be 1/4. It's not exactly correct because the red is a bit larger than the blue, but let's say these bars, the height of this bar inside the chart, so the fraction of bar that is colored green inside each bar correspond to the posterior probabilities of the points in that bin being assigned to the corresponding cluster. So we see that points in each bin give a contribution to all the clusters. Then how do we estimate the samples? We treat these as fractional points assigned to the class. If you want, it is what I was trying to do in this picture. I don't know if I managed, but that's because that's not that easy to draw. I'm taking each of the fraction of points assigned to each cluster, and then I can imagine that what I'm doing is similar to fitting my Gaussian to a data set which would have the corresponding sample. So if I look at it from the point of view of a histogram, I can imagine that if fractions of points have been assigned to samples, if I have lots of points in a bin, that's more or less similar to saying I have this amount of points assigned, this overall amount of points assigned to that cluster. The equivalent number of points is the sum of the fraction of samples that have been assigned. Then I can draw that as if it was a histogram. You see the 3 overlapping histograms that corresponds to the equivalent histograms of the fraction of points assigned to each class. At the beginning, they overlap a lot because essentially I'm extracting these 3 histograms and then showing them one on top of each other rather than stacked. So it's these three histograms extracted from the image with the base of the bars all shifted down, and the size of each bar resized so that each histogram now integrates to 1, so it represents a density. And what I'm trying to do, essentially, I can think of my process as I'm fitting a Gaussian density to each of these histograms, which corresponds to fitting a Gaussian model using the weights. Essentially, I have these fractions of points that behave like, from the point of view of histograms, they behave like if they were an equivalent number of points in that region of space, and it's as if I was fitting a Gaussian to that equivalent number of samples. And this is the result that I get once I do the fitting. Of course, here the result is still fairly bad, but you can see that the densities have moved a bit. Then I can repeat the process. If I repeat the process, you see that this picture changes a lot, the other do not, because I didn't change my model that much. So we may wonder whether this will do something, but if we keep iterating, we will see that at some point, the green will start to move in position, the blue as well, and the red as well. We can see that at some intermediate iteration, all the components will still be affected by all the points, but we see that points in this region will affect the green cluster very little, points in this region will affect the blue cluster very little, and on the other hand, the red cluster, which is somewhere in between, is affected still by points in both regions. But in any case, the majority of the weight for the red class comes from this region. And we can see that indeed, when we try to plot, it's as if we were plotting when we try to estimate the new components, it's as if we were fitting a Gaussian to the red histogram and equivalently for the other two components. When we put everything together, this is what we get. If we keep iterating, we will see that at some point, the 3 will move in place. And what's changed with respect to before? There are regions where points are assigned as fraction to both, to more than one cluster. So we never find a solution where all the points are assigned to a single cluster. Even at the point where we stop, there will be points that will be assigned to different clusters, but that makes sense. In an optimal solution, there will still be points that are somewhere in between two different components. You see here we have two components that have similar weight. To which component I should assign a point that lies exactly here? Both have the same probability of being responsible, that's why it's called responsibilities, for generating that point. So it makes sense that points that are here each point that lies here is half assigned to the red and half assigned to the blue. That's exactly what we get here. These two bars have more or less the same height. But you see that the overall effect is that now, since I'm correctly considering fractional points, my components will be a good fit to the fraction of points that have been assigned to that component rather than to the points. Well, if you compare this with what we had with the hard assignment, we will see that the issues were mainly coming from the red and the green component. We were not fitting very well the corresponding histogram. Now we can see that the red point is a good fit, but not for samples. Now it's a good fit for the fraction of samples that have been assigned to the red cluster, the same for the green, and the overall result is a model that describes much better the overall distribution of my samples. This looks very close to the density that we had at the beginning. It took more time to get there, but now we get, so if you look at the number of slides we had to go through to get there, it's much longer, but now we have a much better solution. We can compare the two. We can see that we could compute the likelihoods actually to prove it, but we can see that already visually that it's much better. Here and here, the second is much better. Here we don't undershoot the density. Here we don't overshoot again. Here we gain a bit, not that much, but still it's slightly better. And we can also see that it goes down better on the tails. The tails are better described by this model. And if you want to put some numbers, these are the weight parameters, the mean and the variance parameters of the three components. Which component? The first one is the real component. The first line is the PDF, so the one that I used to generate the samples. So the samples were generated with these parameters. The second one are the estimate of the parameters obtained by the first iteration, which we see for the weights. It's not that bad, but still it undershoots the weights for the second component by almost 10%. For the means, we can see that it's even worse. It misplaces the mean a bit, and the things become even worse for the variances. The variance of the red component is significantly smaller than what it should be. On the other hand, if we look at the EM solution, called EM, but it's maximum like, so I call the EM because I'm anticipating what we will see later. This algorithm that we saw is called expectation maximization. I didn't say it yet, but we will see why later or probably next time. We can see that it's doing a much better job. Now, we will need to prove that this works, but since it's already quite late and next time we will also have laboratory on this, I want to say everything there is to say on the laboratory part. So we'll skip these slides for the moment, and then next time we'll go back to them to prove that this, what we said now actually converges to at least a good solution in most of the cases. But for now, take for granted, if you want, you can already read the proof, but we can prove that this procedure will increase the likelihood until it reaches a point where the likelihood is flat. So a saddle point of the likelihood, which hopefully will be a local maxima. But in any case, as long as the likelihood is not flat, this algorithm will keep increasing the likelihood at each iteration. So we don't risk, when we move from solution 0 to solution 1, this will result in an increase of the likelihood. When we get solution 2, we will again be increasing the likelihood. So at each step, this procedure guarantees that we are increasing the likelihood unless we are at convergence. We'll prove it next time, if we have enough time, but I hope so. But what we still need to do is we'll say this in a moment. We still need to say how to initialize the model. If we change the initialization, of course, this will change the local maximum we will find typically. As in k-means, we know that in k-means, changing the initialization will change the solution. We know that GMM is a generalization of k-means, so our first possible way to initialize our GMM is to use k-means. So we use k-means to find centroids, and we set initial covariance matrices to be the identities. So this will be the initial parameters. And the weights are equal to 1 over k, and then starting from these values we will iterate. So we will use k-means already to find the solution. Of course, this shifts the problem on how we initialize k-means. So let's not follow this strategy and let's use another solution. Now, the GMM with one Gaussian is easy. The GMM with one Gaussian looks like what? If we have one Gaussian, it's W1 Gaussian, but the sum of the W's must be 1. In this case, I have only one W, so it must be 1. So the GMM with one component is exactly a Gaussian density. We know how to estimate in cross-forward solution the expression for a Gaussian density. Now, what we will see now is a way to start from a Gaussian model with a given number of components and increasing the number of components. So What we will do now is we will adopt a procedure that will operate like this. We start with a Gaussian model with G components. We'll use a procedure that will give us a model which has between G plus 1 to 2G components. We will actually just see the example with 2Gs, but it can be generalized to give any number between these. And then this will use these as initial parameters for our maximization procedure. Then, to generate a Gaussian component with, for example, 256 components, we will do what? We will create an initial model with one component, then we will train a model with 2, a model with 4, a model with 8, until we reach a model with 256. How? Well, let's see all the steps. One possible way to go from one component to two components is to take the GMM component and split it into two. So imagine I have a GMM, for example, with two components, which there I draw as a GMM. Here I draw the single components. This has weights W1 and then W2, mu2 and mu1, and then sigma 1 and sigma 2. I can generate a Gaussian model with two components which doesn't significantly change the shape of the initial model by doing what? I create a new model where the first component is split into two closed components, each with half weight. Now, if this epsilon is small enough, the global shape will remain similar. We will not want epsilon to be too small, because if it's too small, it will take longer than to train the model. But we can imagine that if we split these two components by a small amount, and we keep the same, the covariance matrices, and each gets half of the weight, the sum of two very close Gaussians will have a shape that is similar to a Gaussian that has twice the weight. Will not be very different. So we can start from a component, a Gaussian with G components, and split each component in this way to find two new Gaussians. Now, in one dimension, it's easy because there is only one possibility for splitting. I add or remove a constant. In multidimensional, it's harder. If I have a Gaussian like this, I can split it into two, but should I split them in this direction? Should I split them in this direction? Should I split them over this direction? Over which direction I should move the means? When I add and remove a constant, I'm essentially moving them apart on one direction. Which one? Well, we use heuristics. If a Gaussian model has a large covariance direction over a large variance over one direction, that is probably a direction where it's worth splitting. Why? Because typically it may be a case where that Gaussian is covering two clusters, that the model didn't have enough components already to cover those two clusters with two components, so I moved a single component to cover a large region of space. If the variance is large, there is a good chance that these are two different heterogeneous subclusters that are being covered by the same Gaussian. So it's a heuristics, of course. It's not necessarily the best, but a good value for the displacement will be the direction given by the first eigenvector of the covariance matrix. That is the directions over which the variance for that component is maximum. In laboratory, we'll do this. We'll take the covariance matrix of each component, take its leading eigenvector, and move by a fraction epsilon in that. So our movement will be actually epsilon W vector, where W is the eigen plus or minus eigenvector of sigma C, the max eigenvector of the covariance matrix. Then it's not sufficient to split. When we split, we said we get a model that is similar to the original one, but the original one was optimal for the number of components. With additional components, we may do better. So how will the full procedure work? We start with one component. For one component, it's easy. The maximum likely solution, we know how to compute it. It's a Gaussian. So the problem with one component is already solved. We know how to fit a Gaussian to the model. Then we will have two components, each with half weight, and the mean plus epsilon, and the other will be half weight, the mean minus epsilon. This is 1/2 because the original weight for the single model was 1. Now we have a model that looks like this. These will be the initial parameters for our training procedure. This is the initial model that we have for our training, the initial parameters for the two components GMM. We run our procedure that we called EM now. We said it's called EM. We'll see why it's called EM next time, but the procedure where we iteratively compute responsibilities, update model parameters, responsibilities, update model parameters, and so on, will proceed until we reach some criterion that tells us that the model is converged. Essentially, we look at how much the likelihood increases at each iteration, and then we will stop when we reach that the likelihood does not increase significantly anymore, and this will give a solution that has a local maximum for the likelihood for a two components GMM. If we deem the two components are not enough, we will again split each of these. Notice that we may only split one. We may decide, for example, to split only the one that has highest weight. Remember that high weight means that the Gaussian is associated to a large fraction of points. So probably it's modeling, either we have very imbalanced subclusters, or it's trying to model more than one subcluster at the same time. So it may be worth splitting only those that have large weights, or we may split all of them. Again, all these are heuristics. We will need to find a good strategy and check with a validation set that our strategy is actually good. But let's say we split everything. We split both. Each will take half weight of the original component because the sum of the weights must be equal to 1. If we don't split by much, we are not changing by much the shape of the GMM. So this will be similar to the two components optimal solution, but not exactly the same. We need it to be different because if we split and the two components have the same mean, then the algorithm will be stuck in a local maxima that cannot progress to a better solution already at the beginning. So we need this split to be non-zero, otherwise we end up with a model. We start the model from a bad local maxima for the new model. But if the split is not too large, but sufficiently large, we'll see how to make it reasonably large in the laboratory. This will be our initial model. Then we can train our update procedure and get to a solution with 4 components, which not necessarily describes the original 4 components that were used for the dataset. It describes the cluster that the model was finding. Here I would have a better solution if I had 2 Gaussians like this, rather than, you can see only 3 here because essentially 2 are very similar. So in the global shape, they look like there is a single component, but there are actually 2 that have similar mean and similar variance, so they overlap when you put them together. So this has 4 components. Probably with a different initialization, I may have recovered the original density that was used. So it's a local maximum of the likelihood. We have never guaranteed that we will find the best possible solution. But in any case, we can see that we obtained a reasonably good approximation of our density. How many Gaussians do we use? Well, the more Gaussian we use, the more complex the model becomes. The more parameters, the more the risk of overfitting. So when should we stop the number of components? Well, we can't do that based on the likelihood. If we add components, unless we add them, unless we exaggerate where we split them, but if we do it in a reasonably way, essentially enlarging the number, increasing the number of components will typically increase the likelihood. The model becomes more powerful. It can always find a solution where half of the components have weight 0, and that would correspond to a model with less components. So if we keep adding components, the local maxima that are non-degenerate will increase in value. So we cannot use that as a criterion. There are some criteria that have been proposed that essentially make a trade-off between the likely increase and the number of parameters that we put in the model. But as usual, for us, the strategy we will use will resort to cross-validation. We are using GMM for something, then we will use the GMM for that something, and we will monitor as a function of the components how that something will change. Then we need to pay attention to the generate models. We see in the laboratories how to avoid this. Then a few words that I wanted to say. I don't have the time to say everything, but I wanted to say just these two things because we will need them for the laboratory. How do we use GMM for classification? Essentially, I will come back to this. We'll do the same thing we did with the Gaussian, but with the Gaussian model, we said what? Each class is described by a Gaussian model. Now we say each class is described by a GMM model. So we will fit as a first approximation a GMM to each class, to the samples of each class independently. So we will do it as for the MVG. We will not tie the parameters because that will make things more complex. We could, but we will not. So we will consider each class is represented by its own GMM. The GMM of the different classes may even have a different number of components. The number of components, well, it may be good to tune the number of components based on what we know on the dataset. If we know the dataset has 5 or 6 clusters, then it may make sense to try GMM with 4 to 8 components. If we know the clusters, we look at the data, we see that there are hundreds of clusters, then we may want to use GMM with hundreds of components. Of course, the exact number will tune by cross-validation, but essentially, each class, the samples of each class will be modeled by GMM. We'll fit a GMM for each class, and then we will use that GMM to perform inference. So we will learn the GMM associated to each class, and then we will proceed as in the MVG model. Given the GMM for each class and the test point, we will compute class posterior probabilities. Class posterior probabilities are what? Are the joint for class C. Now this is a class conditional and prior for the class, divided the sum over the classes. Now this GMM, these are class labels for classification. This GMM itself will be a weighted sum of components. What was in the Gaussian model here a Gaussian density for class C, now we will have a GMM for class C. Nothing else changes. Once we have defined how to train a GMM for one dataset, we will use that repeatedly for all the samples of the different classes. So we'll estimate, if we have 3 classes, we will estimate 3 GMMs for the different classes. And then we will implement the function that computes the likelihood for a GMM given its parameters, and then we will do inference exactly as in the MVG model, rather than having here Gaussian PDF for the model parameters for class C, we'll call the GMM PDF with the parameters of the GMM for class C. Nothing else changes afterwards. So the rest of the inference remains exactly the same. Then we will see some variations of the model that, since they are not difficult, I will introduce directly before the laboratory. Before the next lecture, it's not really changing much. And then next week, we will also see, well, the proof that this converges. And we will also see how to use the model for open set classification. We will not be using this for the laboratory, but we will see how this is a first model that finally allows us at the end of the course to start talking about open set classification problems. Questions? Okay, then we can take 10 minutes break and then move to the lab.